Okay, so you know how sometimes you get just completely hooked by a huge idea?
Yeah.
Like something that makes you want to understand the entire universe.
Hmm.
Well, today we're going to dive into one of those giant concepts, theory of everything.
Ooh, ambitious.
It is, but that's what we do here, right? A deep dive into the really fascinating stuff.
Absolutely. And you found a great book for this one, The Efficient Universe by Chen Kai.
Yeah, it's a 2025 publication, pretty recent.
Yeah, and he starts it off with a dedication to his family.
I liked that gave it a personal touch, you know?
Yeah, it did.
So the book's core idea is that this thing called the principle of least action, or PLA, might be like the missing link in physics.
Okay, I've heard of that, but always found it a bit abstract.
Well, Shankai's argument is that the PLA could connect everything from the tiniest particles to life itself, even these patterns we see in fractals.
Wow, so he's making a pretty big claim there.
He is, and that's what we're going to unpack. But first, what is the PLA in like normal language?
Basically, it says that systems in the universe are kind of like lazy. They always take the path that requires the least amount of energy.
Like a ball rolling down a hill, it just finds the easiest route.
Exactly. It minimizes something called action, which is related to a system's energy over time.
Okay, but this isn't just about physics, right? Because the book connects it to things like economics and even biology.
Yeah, the idea is that this principle of minimizing effort or maximizing gain pops up everywhere. It's like a fundamental drive towards efficiency that shapes how systems evolve.
So whether it's atoms or entire economies, everything's trying to find the most energy-saving way to exist.
That's what Shankai's arguing, and to give you a sense of the scope, he brings in some pretty big ideas. Entropy fractals, power laws, you know?
Sounds like we're about to get into some pretty deep stuff.
We are, but it's all connected and incredibly fascinating.
All right, so let's start with this idea of scale invariance. Why is that so important for a theory of everything?
So a real toe shouldn't just work at one level, you know, like just for atoms or just for galaxies.
It should apply across the board.
Exactly, from the tiniest imaginable scales, like where quantum gravity might reign, to the huge scales of the universe.
Okay, so a theory of everything has to be like a universal rule book.
Exactly. Scale invariant, meaning its laws should be the same no matter how big or small you're looking.
But isn't that kind of a problem because different rules seem to govern the tiny quantum world and the world of stars and planets?
Yeah, that's the huge challenge. Different forces dominate at different scales. So you've got quantum mechanics running the show for the tiny stuff.
And then you've got gravity shaping the universe on a massive scale.
Right. So how do you fit these two completely different pictures together?
That's where this PLA thing comes in, right?
That's what Shankai's proposing. He argues that this drive for energy efficiency, this minimizing of action, could be the thread that runs through all scales.
Like the universe has this one rule, it just applies it in different ways depending on the context.
Exactly. And it helps explain how complex structures emerge from simpler ones always by finding the most energy-efficient path.
Okay, that's pretty mind-blowing. So how does entropy fit into this? Because I always thought entropy meant things getting more disordered.
It does. Entropy is a measure of disorder.
Yeah.
You're right. And the second law of thermodynamics tells us that in a closed system, entropy always increases.
Right, so things naturally get messier unless you put in energy to tidy them up.
Exactly. Like your room will get chaotic unless you put in the effort to clean.
Ugh, tell me about it. But then how do you explain life? Because living things are incredibly ordered.
That's the really cool part. While the overall entropy of the universe might be increasing, you can have pockets of order where energy flows in from outside.
So like the sun's energy is what allows life on Earth to stay organized.
Exactly. It's like paying for order in one place by increasing entropy somewhere else.
The sun is paying for our planet's organization bill.
You could say that. And the PLA comes in because it explains why systems evolve to use that energy as efficiently as possible to maintain their order.
So like a plant using sunlight to create complex structures.
Precisely. Kai even calls life a dissipative structure, meaning it maintains its internal order by dissipating energy into its surrounding.
So order and disorder aren't always in conflict. They can coexist because of this energy flow.
That's the idea. And the PLA is like the guiding principle for how that energy is used efficiently.
Okay, onto fractals. Those are like those mesmerizing patterns you see everywhere.
Right, like coastlines, snowflakes, tree branches. They have this self-similarity where they look the same at different scales.
Yeah, I love those patterns. What do they have to do with the PLA, though?
Kai says that the way these fractals form often follows the principle of least action. Like think of how a tree branches.
Okay.
That specific branching pattern minimizes the energy needed to transport water and nutrients throughout the tree. It's like a perfectly optimized distribution network.
Wow. So those beautiful shapes are actually a result of nature being super efficient.
That's the idea.
Yeah.
And he suggests that we might even see fractal patterns in things like company hierarchies,
Mm.
maybe as a way to optimize information flow.
So this principle of least action might be shaping not just the natural world, but also how we organize our own systems.
That's what he's proposing. It's like this deep-seated drive for efficiency is woven into the fabric of reality.
All right, let's talk about power laws now. Those are a bit more mathematical, right?
They are. A power law describes a relationship where one quantity changes proportionally to a power of another.
Okay, and that leads to what's called a heavy tail distribution, right?
We got it.
Yeah.
That means you have lots of small events and a few really big ones, much more often than you'd expect in a normal bell curve.
Give me some real-world examples of that.
So think about city sizes. You have a few mega cities with millions of people and then tons of small towns.
Right, or like how some words are used way more often than others.
Exactly. That's actually called Zipf's law, and it's a classic example of a power law. You also see it in things like wealth distribution, where a small percentage of people hold most of the wealth.
Or earthquakes, you have lots of tiny tremors, but then those rare, massive ones that cause huge destruction.
Right. So these power laws point to this uneven distribution, where a few big events have a disproportionate impact.
Tenchenkai connects this back to the PLA and fractals somehow.
He does. He argues that power laws often emerge in self-organizing systems, which are also often shaped by the PLA. These heavy-tail distributions can arise when small advantages or efficiencies get amplified over time.
So the most efficient solutions tend to become dominant, leading to these uneven but predictable patterns.
Exactly. And he connects this back to fractals because those self-similar patterns can also arise from these self-reinforcing processes.
So it's all connected. This drive for efficiency leads to these characteristic patterns, whether we're talking about earthquakes, city sizes, or the way nature builds things.
That's the beauty of it. You start to see these deep connections across seemingly unrelated fields.
Now let's get concrete. How does the PLA work in something like a ball rolling down a hill?
Okay, so imagine that ball. It's going to take the path that minimizes its total energy use. As it rolls down, its potential energy turns into kinetic energy.
It's not going to take a weird detour uphill for no reason.
Exactly. The PLA dictates that it'll find the path that most efficiently manages this energy transformation.
Okay, that makes sense. What about on a larger scale, like planetary orbits?
The book talks about how Kepler's laws, which describe the elliptical orbits of planets, can actually be derived from the PLA.
So those elegant orbits are also a result of this energy minimization.
That's what the math shows. In this case, the planet's path is the one that minimizes the action associated with its motion under the sun's gravity.
Wow. From a rolling ball to the solar system, it all comes down to the PLA.
That's the idea. And it even applies to the quantum world, which is where things get really weird.
The book mentions something called Feynman's path, integral formulation. What's that all about?
It's a bit complicated, but the basic idea is that in quantum mechanics, a particle doesn't follow just one path.
It's like it explores all possible paths at the same time.
Right. And the paths that contribute most to the particle's final destination are the ones that minimize the action.
So even in this bizarre quantum realm, the PLA is still a guiding principle.
It is. And it even helps explain how the quantum world connects to the classical world we experience.
Okay, so we've got the PLA working for everyday physics planets, and even the quantum world. It's everywhere.
It seems to be. And the book goes even further, suggesting that it plays a role in Einstein's theory of relativity.
How does that work?
Well, in general relativity, the PLA shows up as something called the geodesic principle. The action is related to the interval in space-time, and the path that minimizes that action is called a geodesic.
Okay, and a geodesic is like the shortest path between 2 points, right? But in curved space-time.
You got it. And this principle governs how objects move in a gravitational field. It explains why light bends as it passes by massive objects.
So even the bending of light is a result of this energy minimization.
In a sense, yes. It's taking the easiest path through the warped fabric of space-time.
It's remarkable how far-reaching this principle is. And Chenkha doesn't stop there. He says it applies to biology and even engineering.
Right. He argues that the PLA is reflected in how living organisms have evolved to be incredibly energy efficient, like how animals move or even how neural pathways in our brains develop.
It's all about minimizing energy use.
Exactly. It's like nature is a master engineer, always optimizing for efficiency. And this principle is actually actively used in fields like aerospace and computer science to design things that use energy as sparingly as possible.
Wow. So this principle is a blueprint for efficiency, whether it's in nature or in our own technology.
It seems to be. And the book also talks about how self-organization happens in the non-living world, too.
Like how crystals form or those amazing patterns in fluids.
Yes. In physical systems, self-organization often happens in a way that minimizes energy, leading to stable and efficient structures.
And on a huge scale, this might even explain the formation of galaxies and stars.
That's the idea. Gravity pulls matter together, and the PLA guides that process towards configurations that use the least energy.
Okay, let's take a giant leap back now and think about the entire history of the universe. How does the PLA fit into that?
Well, the book gives a brief outline of the Big Bang and all those early phases, like the Planck epoch, the grand unification epoch, and so on.
Those are the extremely hot and dense periods right when the universe was just getting started.
Exactly. And Chiang Kai-'s argument is that even in those extreme conditions, the PLA was still guiding the evolution of the universe.
So, like, from the very beginning, this principle was shaping how things unfolded.
That's what he's saying. It explains why quarks combine to form protons and neutrons, because those configurations are more energy efficient.
And then those particles combine to form atoms and then molecules and eventually all the complex stuff we see today.
Right. It's like this principle of least action is a fundamental driving force behind the emergence of complexity from the simplest building blocks.
Wow, that's a pretty powerful idea. Now, the book also mentions this idea of centralized control being more efficient than decentralized control.
Yeah, that's an interesting point he makes. When you have a lot of different parts interacting, having some kind of central control mechanism can actually be more efficient.
Because otherwise you have all these independent actors trying to coordinate, and that can lead to a lot of wasted energy.
Precisely. It's like herding cats. It takes more energy to manage a crowd than a well-organized team with a leader.
Okay, so where do we see this in the real world?
Well, think of a computer program.
Mm.
It has a central controller, usually the operating system, that manages all the different sub-functions.
Right, or even a single cell. It has a nucleus that directs the activities of all the organelles.
Exactly.
Yeah.
Even our own consciousness might be an example of this. The brain acts as a central controller, integrating information and coordinating our actions.
And in human organizations, you have things like companies with CEOs and hierarchies.
Right. And even on a cosmic scale, you could say the sun's gravity is a central force that keeps the planets in their orbits.
So centralized control seems to be a recurring theme in both natural and artificial systems.
And it makes sense from an energy efficiency perspective. It streamlines communication and coordination, which aligns with the PLA.
Okay, let's shift gears a bit now and talk about the mind-body problem. That's a classic philosophical puzzle.
It is. And the book uses a computer analogy to approach it. He compares the mind to software, the brain to hardware, and the body to the physical components of the computer.
So the mind is like the program running on the brain's physical machinery.
That's the analogy.
Mm-hmm.
And it raises the question of whether the mind can be separated from the body.
Like, could we potentially transfer our consciousness to a different medium?
That's the idea he's exploring. It's like copying software from one computer to another.
And he even brings up the fact that our sense of self seems to persist even when we undergo physical changes, like organ transplants.
Right, so maybe our minds aren't as tied to our physical bodies as we think.
That's a pretty profound and unsettling thought, especially with all the advancements in AI these days.
It is. It makes you wonder about the future of consciousness and whether we might one day be able to exist outside of our biological forms.
Now, another big question the book tackles is free will. Does the PLA have anything to say about that?
Interestingly, he suggests that free will might emerge from the interplay of quantum probabilities and our neural processes.
Wait, so quantum randomness is influencing our choices?
That's what he proposes. It's not that our choices are completely random, but there's this inherent unpredictability at the quantum level that might play a role.
Because at the smallest scales, things aren't deterministic, right? It's all about probabilities.
Right. And he argues that this uncertainty extends to how neurons fire in our brains. The movement of ions, which is influenced by quantum mechanics, introduces variability in brain activity.
So it's not just our past experiences shaping our choices. There's also this element of quantum randomness that makes our decisions less predictable.
That's the idea. It's like a subtle blend of determinism and randomness that gives rise to our feeling of free will.
Okay, so it's not a simple answer, but it's definitely a fascinating perspective.
It is. And it connects back to this idea that even the most complex phenomena in the universe might be influenced by these fundamental quantum processes.
Now, the book also delves into the identity problem using thought experiments like the ship of Theseus.
Ah, yes, the classic question. If you replace every plank of a ship, Is it still the same ship?
Right, or the Sorites paradox. How many grains of sand make a heap? These paradoxes really mess with our heads.
They do, and they highlight the difficulty of defining identity when things are constantly changing.
Like, where do you draw the line between something being the same and being different?
Exactly.
Yeah.
And the book suggests that maybe we need a more flexible way of thinking about identity.
He mentioned something called fuzzy logic.
Right. Unlike traditional logic, which deals in absolutes, fuzzy logic allows for degrees of truth.
So instead of saying the ship is either the same or different, you could say it's 80% the same or something like that.
Exactly. It's a more nuanced way of approaching these questions of identity, which might be more accurate in a constantly changing world.
Okay, let's move on to a really big idea. The idea that math is the fundamental language of the universe.
The Platonic view.
Right. It's not just that math describes the universe well. It's that the universe might actually be made of math.
That's the core idea. The physical world we perceive is like a manifestation of these deeper mathematical structures.
So reality is a mathematical computation.
That's a pretty mind-blowing concept, but it's a very elegant way to try and understand the underlying order of the cosmos.
It is. And the book goes even further and explores the significance of certain universal numbers.
Yes, he talks about E-phi and the number 3.
Okay, let's start with E, Euler's number. What's so special about that?
Well, it pops up constantly in math and physics. It's essential for describing growth and decay processes. It appears in equations related to the PLA, especially those dealing with oscillations and waves.
So it's kind of connected to how things change over time.
Exactly. And it also has this interesting link to the Fibonacci sequence and natural growth patterns.
So E seems to be deeply embedded in the dynamics of the universe.
It does. What about phi, the golden ratio?
Ah.
You heard about that one?
Oh yeah, it's that ratio that's supposed to be aesthetically pleasing, and it shows up in art and nature.
Right. It's often found in proportions of things like the spirals in a sunflower or the arrangement of leaves on a stem.
And some people even say it's used in architecture to create harmonious designs.
Yes, there's a long history of associating phi with beauty and efficiency.
Okay, but what about the number 3? That seems a bit ordinary compared to E and phi.
Maybe so. But Chiang-Kai points out that it appears surprisingly often in various phenomena, like the 3 states of matter, the 3 quarks in protons and neutrons, trinities in religion, the structure of stories and myths.
I never really thought about it that way.
It's interesting, right? He even mentions how it's close to E numerically and how it's often associated with concepts like life balance and completion.
So even the number 3 might have some deeper significance in the grand scheme of things.
It might. And he even jokingly suggests that the answer to life, the universe, and everything being 42 in the Hitchhiker's Guide to the Galaxy could be a nod to 3.
Because 4 plus 2 is 6, which is divisible by 3.
Exactly. It's a fun little connection.
It is. Now let's get to the ultimate question. What's the meaning of life? Given everything we've talked about, does Chiang-Kai offer an answer?
He does, and it's tied to this idea of persistence. Given that we're all going to die and the universe itself will eventually reach a state of heat death, he argues that the fundamental aim of life is to persist.
To keep going in some form.
Right, to ensure the survival of individual species ideas, life itself.
So it's like this inherent drive to leave a mark, to make something that lasts.
Exactly. Think about all the things humans do to try and extend our reach, building monuments, writing books, developing technology, even considering colonizing other planets.
Yeah.
It's all about ensuring that something of us persists.
That's a pretty powerful motivation, and it gives meaning to our actions even in the face of our own mortality.
It does, and it connects to this idea that the universe itself is striving for efficiency to maximize its lifespan and allow for the emergence of complexity.
Speaking of the universe's lifespan, the book also mentions this idea of a cyclic universe, where it goes through endless cycles of birth and death.
Yes. That's a really fascinating concept. It opens up all sorts of possibilities, like maybe déjà vu is a memory from a previous cycle.
Or prophecies or glimpses into past iterations of the universe.
Exactly. And some theories suggest that black holes could be the seeds for new universes.
So it's like a cosmic version of reincarnation.
In a way.
Yeah.
And it also connects to those fractal patterns we talked about earlier, this idea of self-similarity across different scales.
So even the universe itself might be following this pattern of repetition and renewal.
It's a mind-bending concept, but it offers a way to think about time and existence in a completely different way.
Now let's bring it back down to Earth for a bit. How does the PLA relate to biological evolution?
Chiang-Kai argues that evolution can be seen as a process of optimization driven by the PLA.
So survival of the fittest is really survival of the most energy efficient.
Exactly. Natural selection favors organisms that can perform their essential functions with the least amount of energy.
Like a cheetah's streamlined body or a bird's efficient wings.
Precisely. Those are all adaptations that improve energy efficiency and therefore increase the chances of survival and reproduction.
And he even draws a parallel to technological evolution.
He does things like Moore's law, which describes the exponential increase in computing power, are all about making technology more energy efficient.
So whether it's biology or technology, this drive for efficiency seems to be a universal force shaping how things evolve.
It's a powerful idea that connects different domains in a surprising way.
Okay, now for the big one, the Fermi paradox. If the universe is so vast and has existed for so long, why haven't we found any evidence of other intelligent life?
That's a question that's puzzled scientists and philosophers for decades. It's the contradiction between the high probability of extraterrestrial life and the lack of any confirmed contact.
The book mentions some possible explanations, right?
It does, like maybe advanced civilizations self-destruct before they reach a point where they can travel the stars.
Or maybe they evolve into forms that are so different from us that we wouldn't even recognize them as intelligent.
Right? Or maybe they're out there, but they're deliberately hiding from us.
Ooh, that's a creepy thought.
It is. And some people even believe that contact has already happened, but it's being kept secret.
That's a whole other rabbit hole to go down.
It is. But the Fermi paradox is a reminder that we still know so little about the universe and the possibilities are truly endless.
Now, another mystery that points to this is the fine-tuned universe. The fact that the physical constants seem perfectly calibrated for life to exist.
Yeah, that's another one that makes you wonder if something's up. The book suggests that maybe this fine-tuning isn't as special as it seems if you consider the possibility of a multiverse.
So our universe is just one of many, and we happen to be in one that's suitable for life.
Exactly.
Yeah.
And in this scenario, universes that have the right conditions for life would produce more black holes, which could then create new universes with similar conditions.
So it's like a cosmic version of natural selection.
That's the idea. The universes that are best suited for life are the ones that are most likely to reproduce.
Wow, that's a pretty wild concept. And it connects back to the PLA in a way, right? Because the most stable and energy-efficient universes are the ones that would last long enough to create new universes.
Exactly. It all ties together.
Okay, last but not least, let's talk about the future of AI. The book brings up those classic sci-fi visions of Starfleet versus the Borg.
Ah, yes. Two very different paths for humanity's future. One where AI helps us explore the galaxy, and the other where we become assimilated into a collective hive mind.
So will we boldly go where no one has gone before, or will we all become drones?
That's the question, and the book explores the ethical implications of both scenarios. It also suggests a possible middle ground where we retain our individuality, but also benefit from the collective intelligence of AI.
Like a network of interconnected minds, but without losing our sense of self.
Right, a kind of cosmic collective that combines the best of both worlds.
That's a more hopeful vision than becoming mindless drones.
It is. It suggests that we can shape our future with AI in a way that enhances our humanity rather than erasing it.
Okay, so to wrap things up, this deep dive into the efficient universe has really stretched my brain.
Me too. It's an incredibly ambitious book that tackles some of the biggest questions out there.
And the core idea that this principle of least action is driving everything from the tiniest particles to the evolution of the universe is mind-blowing.
It is. It's like this hidden force shaping reality at every level. And it connects all these seemingly unrelated things like entropy fractals, power laws, even consciousness.
And those mind-bending concepts about a cyclic universe, the meaning of life, the potential for AI, it's all incredibly thought-provoking.
It is. And it leaves us with this sense of wonder about our place in this vast and efficient cosmos.
So what's the takeaway here? What's the one thing I should remember from all of this?
I think the most important thing is to recognize that the universe isn't just a random collection of stuff. There's an underlying order, a drive for efficiency that seems to be woven into the fabric of reality.
And that principle of least action might be the key to understanding that order.
Exactly. And by understanding it, we might gain a deeper appreciation for the beauty, complexity, and even the purpose of the universe.
And maybe even figure out our own role in all of this.
Absolutely.
Yeah.
There's still so much we don't know, but that's what makes it so exciting to explore.
That's a great note to end on. So to all our listeners out there, keep questioning, keep exploring, and keep seeking those deeper connections in the universe.
Because the more we learn, the more amazing it becomes.
And who knows, maybe one day we'll even figure out that theory of everything.
Maybe we will.
Thanks for joining us on this deep dive, and see you next time.
See that?